Very nice. So, have good afternoon, everyone. My name is Philip, and I'm going to talk 1 hour about why I think this pile of poo should have a length of 1, and why JavaScript and many other languages think it should have a length of 2 or 4 or whatever. We'll see. Now, where is the problem? I mean, if you look at the length of an empty string, you would get 0. By the way, this is JavaScript code, but this also works in Java. And it also works in Objective-C. It also works in many other languages. The length of A is 1. The length of A, also 1. So what is the problem? I can run this on Node. See here, why am I even here? Where is the problem? Well, the length of the musical sign apparently is 2, and the length of the pile of poo, of course, also 2. What? I guess to answer this question, we need to know what are we actually counting. I mean, JavaScript told us that that thing has a length of 2. So, I mean, it could be that it's just a bug. I don't think so. I think the length of string is normally correct. So maybe it's counting something else that we think it's counting. But before we can do that, we need to get even more fundamental, because we need to talk about what is a string. Because computers are, well, they're called computers, so they're really good at numbers. They're incredibly good with numbers. They can add them, multiply, whatever, but they're not so good with text. Humans, on the other hand, extremely good with text. And then you have marketing departments that say, hey, if you want to sell your software, you should probably work with text. So we kind of need to translate what humans want to do over to what machines can do. And, you know, when all you have is a hammer, then every problem looks like a nail. So what were we doing? We were converting these numbers into text by just creating a mapping. So we were saying, okay, the number 65, let's say that's A. And somebody else that was doing different development was saying, number 65, that's probably C, whatever. So you have this thing in memory, you know, this number has this meaning, this number has this meaning. And when you eventually you want to store that text that you have somewhere, and then what do? You take it, you have your thing in memory, you write it to disk, then it's on the disk, and then sometime later you want to read it again. What do? You read it from disk, there it's in memory. Problem solved, hey, we can deal with text. This works really well until you have to move between different machines. In the early days, you built your machine. I mean, you really soldered and, do this stuff. And everybody had their own idea. For someone, 65 was A, and for others was C or whatever. So we need to fix this. And the American Standard Code for Information Exchange was published in 1963. So you can see it's really far in the past. It uses 7 bits to encode a character. And it says, okay, those 7 bits have this meaning. Those 7 bits have this meaning. And this is the perfect solution for all our problems, because everybody is using English as their language. So this is perfect, right? Computers were starting to take off. You could say there was once, people said there's a market for 5 of those things. By now, it's a bit more. And also, computers were started to be used outside of just the US. So we needed a solution. I was just really scared for a moment. So we had this ASCII standard. We have 7 bits per character. But most of the machines by now are 8-bit machines. So we can use that other bit. We can double the amount of characters. And so let's do that. And so we started to have, in different countries, we had different meanings for those characters where the first bit is set. Maybe some of you might still remember this. This is what we did in the MS-DOS days to tell the machine how to interpret these numbers that are higher than 127 and what their meaning should be, which was perfect. Unfortunately, the internet has happened, and we had an inherent problem that we didn't have enough characters to even do this. We could not combine in one string the Western European encoding, it's like the first part of the string, and a Cyrillic text, that's the second part of the string. We had a problem, and we needed to solve this. So we have invented Unicode. Unicode used 16 bits per character. That was like specified. Okay, instead of using 8 bits per character, let's just use 16 bits. This was published in 1991. Of course, it had fatal bugs, so we have revised it, 1992. This was seen as the final solution for this problem that we were having, which was we could not move a document from one place of the world into another place of the world, because these different places of the world had a different interpretation of what each number maps to. And so people ran onto this, jumped onto this. Everybody said, hey, we support Unicode now. Microsoft did it with Windows NT, later backported to Windows 98. So everybody said, hey, we do Unicode. Of course, it's the 90s. There were atrocities committed in software engineering. We all know that. So we forgot a few things. Now, one thing is we still wanted to store that string and later reload it. And we haven't really done anything to specify how this process should work. So we still have our string in memory. And if we want to write it, we dump it to disk. And if we want to load it, we load it from disk. And we have a small issue with the byte ordering on these machines. Some of them used little endian, some of them used big endian. It was not defined, so you still had documents that you couldn't move from one machine to the other. We found workarounds for that. I'm talking about this later. Also, because of compatibility concerns, people didn't just extend the existing data types, like char in C, still 8 bits, but they created a new data type that's 16 bits wide. It was called wide char, and that's it. All APIs were adapted to this. The Windows API made a copy of every single API function, added the W at the end, and said, okay, this is our Unicode solution. Java, same thing, but they didn't extend the API because they started with this, but still 16 bits everywhere. Objective-C, JavaScript, everyone. C did it better. They mostly stayed away from this. But you know, this is like perfect. We have 16-bit characters. We can store all of Unicode because a Unicode code point is defined as 16 bits wide. This is perfect, right? We can store 65,000 characters. And clearly, this is enough for everybody for all eternity. Just like 640K RAM were clearly enough for anybody. Yeah, so we had still some issues with Unicode 1. We were still just dumping stuff from memory and reading it back. So we had no way, if we read some text, we have no way to know, is this that I just read 16-bit Unicode? Or is this thing that I just read 8-bit characters like old style? So we don't know because it's all just numbers. From disk, all we read is numbers. 65, 90, 0, 0, 65, and the notion that gives this meaning is all just definition. So we still have this problem, and people have solved it by applying heuristics. So you load something from disk and you look at it, and does it look like it could be Unicode? yeah, okay, then let's use, it's probably Unicode. There's a little trick you can do if you have Windows. Open Notepad, type in bush, hit the facts, save it, close Notepad, reopen it, document is empty. And this is caused by general Unicode issues. And then we also have the byte order mark, was also messy. People probably know about this. Let's not talk about this, please. Eventually, we found out that this can't work. We need to know the meaning of documents that we read from disk and that we store to disk. And so very smart people have invented the Unicode transfer format. You might know it as probably abbreviated as UTF. Especially UTF-8 has happened, which, because it's backwards compatible, was really helpful. And of course, we have also improved the programming environments, so that was helpful there too. But the biggest thing that happened was Unicode 2 and later. Later releases didn't really change much. They just added more characters, added more writing systems. Unicode 2 gives you a theoretically unlimited code space. Right now, it's about 1.1 million characters that are defined. Unicode doesn't talk about bits and bytes. Unicode 2 doesn't talk about bits and bytes. It talks about code points and graphemes, and we're also going to talk about this a bit later. But we're not talking about how this is stored. And the old characters, so what was Unicode 1, lives inside of Unicode 2 in the first 65,000 code points. But the biggest invention, in my opinion, was the Unicode transformation format, because this finally allows us to know how to store Unicode in a way that when we read it back, we can at least see whether the thing we just read was valid or not. This is the biggest change. When I read the blob of data from disk, I know whether this is UTF-8. I don't know if it isn't, then I still have no clue what it is. But at least I have a chance in seeing whether the thing I read is actually valid in the context of what I want it to be. So UTF-8 is the one we all know about. It's an 8-bit encoding to store code points. It's the same as ASCII for the first 127 characters. It uses multiple bytes to encode code points that are like outside of the ASCII range. And the old algorithms that we used for counting string length and indexing into string length don't work anymore, because now we use multiple bytes to encode some characters. So in order to get the length in characters of a string, you really have to scan it from the beginning. There is also UTF-16 that is also using, or it's still using a 16-bit per code point encoding. We have still the issue that in 16 bits, you could only potentially fit 65,000 characters. To extend this, people have invented or taken a few characters out of the first Unicode definition and said, okay, those should be unused, but if they are there, then if they are combined with those other things, then they have this code point as a meaning. This is basically the only way how all these environments I was talking about before, all these bandwagon jumpers that said, yeah, now we have Unicode, it's perfect, how they can even have a chance at going from their limited 65,000 character range to something bigger. We still have issues with byte order. This isn't solved with this, but at least this is a way out for these people. We also have UTF-32. Nobody aside of Python 3 uses this because it's like using 4 bytes per character. You could think, okay, that's enough because then I can really encode any Unicode character. So maybe this allows me to index a string directly. because if I know the size of each character, then I know where to jump to in memory. But because of combining marks, I'm going to talk about those as well, this also doesn't work. So let's step back. What is a string? I can tell you it is not a collection of bytes. The collection of bytes is the thing that you write to disk or write to the network, but a string is, once you have read those bytes and you have run them through some algorithm to decode them, then a string is a collection of graphemes. A grapheme, that's what you would see as like a single character. That is what we would interpret as a single character for a specific writing system. You could also say a string is a collection of Unicode code points. There is a difference, which brings us back to counting. And I still can't tell you what we're counting, because we need to clear one more thing. The character A is not the same as the other character A on this slide. The first A on this slide is a Latin small letter A with a diaeresis. And the second letter A, or the second grapheme in this case, is a Latin small letter A, so that's just an A, followed by a combining diaeresis, or just the two dots that you put on top of the A to make an A. Both look exactly the same for us, not for the machine. So when you count, you could be counting the length in graphemes, which is probably what humans mostly want to do. You could also count the length in Unicode code points, which would, for that other A, would give you 2 code points. Or you could count the length of your binary blob once you have encoded it and you need to write it to some memory or send it off over the network or whatever. Or you do something in between, because you were one of those trigger-happy bandwagon jumpers, and now you have this kind of issue where your APIs do one thing, but you also need to support the other thing. And this is where the explanation for this behavior in the beginning actually lies. So, Java, JavaScript, Objective-C, the whole Windows API, everybody lives in the 90s. Oh, I guess we wish we could go back and fix it. So all these APIs define a string, not like I have them defined before, but as an array of UCS2 or of 16-bit things that are defined as to be interpreted according to the UCS2 standard. The UCS2 standard is that thing that allows a maximum of 65,000 characters to be encoded. That's basically Unicode 1. And because the string are not defined as some abstract thing, but really as a collection of bytes, so the byte arrays are leaking into our languages and into our APIs, we have these APIs that don't understand what is actually going on, because they work on bytes, basically. None of these APIs know about Unicode 2, and we cannot change these APIs because of backwards compatibility. Of course, we still want to support Unicode 2. I mean, I wanted to submit the talk title that had a pile of poo in it. We want to send tweets in languages that have different writing systems. We definitely want to show all these piles of poo. And so we needed a solution. And because UCS2 kind of is a subset of UTF-16, we could just pick some characters that were formerly not used in Unicode 1 and just say, okay, we combine those characters with some other characters, and if those two are combined together, then this forms an algorithm that we can follow to actually leave those 65,000 characters behind and expand our universe to the whole thing. But again, the string APIs, they don't know about this. This is just happening by definition, and you would need specific libraries or updated APIs to actually understand this concept. So let's talk about ECMAScript. Even though all of this is again also valid in Java, Objective-C, C, if you're using like some APIs. So this is like a universal problem. The string methods are leaky. String.length assumes you're using UCS2. So for characters that are inside of the basic multilingual plane, so that's the first 65,000 characters, those return you the length in code points. Again, will be code points, not graphemes. So it might not be so useful because you could still have a problem that your A has a length of 2. And for stuff outside of the basic multilingual plane, it just sees these like code points that were reserved for this expansion and just counts them. So there you get some mixture between the half of the byte length or the code point length. It's kind of annoying. Substring in all these APIs actually can break strings, because they only know about these 16 bits they act on. If you tell these naive substring algorithms, hey, give me the 5th character, they just do go to the beginning of the array and then scan 5 times the 16 bits and return you whatever is there. That might not be a valid character. Character add has this problem, and forget all these to uppercase to lowercase because they just screw it up completely. And this is not like a theoretical issue. I have the string foo, poo, bar that JavaScript believes is 8 characters long, even though foo is 3, bar is 3, and poo I would say is 1, and get 8. It's okay, I mean, string lengths are not so important, but it gets to be a problem when you ask JavaScript, hey, give me the character at position 3. That is half of the pile of poo. So 0, 1, and 2 are foo, and then the third is half of the pile of poo. So now it starts to become problematic because you wanted the third character, you got half of a character. You act on that, you run with this, you try to put that into some database, send it over the network, but you have lost data. And of course, if you ask for a substring, you can also get half of characters. So a bit annoying. Really annoying also regexes. A matches the word character. This some, I don't know, probably Chinese thing doesn't match a word character, even though it is a word character. If you match for any character in that one character, you again get a broken character back. And if you say, okay, in this string that has 1 character in it, does this match 2 arbitrary characters? Then JavaScript will tell you, yeah, of course, here, sure. And it's this like 1 character. So those 2 that you ask for is actually this 1. You have no normalization. Normalization is what you do if you want to unify these interpretations between those like different as. And so I have this UTF-8 encoded file. Yeah, the screen is pretty big. I think you can read it. It's also not so important what it's actually encoded as. It's a fragment of some HTML. It contains 1 string that has the A in it, and the other string that has the A with the following diaresis in it. This is how it looks in HTML. I mean, If you look at the source code in the browser, it looks like that. Yeah, they look similar, but they're not the same. So this makes it really hard if you want to do like string validation and people have these characters in them. And until now, browsers really wouldn't help you there. You would basically have to do this all on the server if you want to do it right. And you know, real world example, I submitted my talk, and if I count opening parentheses, quote, poo, quote, closing parentheses, I count 5 graphemes. And they have this algorithm that like takes strange and not URL safe characters and replaces them with underscores. And they replaced it with 6 underscores, even though that potentially should only be 5 of them. So even in like nowadays, even in today's age, we still get it wrong. Others did better. Python 3, it took them until 3.3 to fix this. They internally, they just say, okay, this is a string. You do not think at all about how this string works. It's just a string. If you need to put it somewhere, if you need to write it out, you have to encode it. And with Python 3.3, they finally started to encode the strings in a way that they know which encoding of UTF-8, 16, or 32 they need to know to use to encode the string in a fixed length. And then internally, they just convert between the two. So a string that just contains ASCII is using an 8-bit encoding. And the moment you add a German umlaut, it's switching that particular string to 16-bit encoding. And once you add a pile of poo, then it's using UTF-32. The advantage is here, Python can do that because you think about strings. You don't think about the in-memory representation of this thing. If you ask Python, give me the 3rd character, you get the 3rd character. You don't get half of it because you're talking about strings. People were really pissed off when Python switched to this, when Python 3 started to do this Unicode stuff, because stuff that was just working right now suddenly started breaking. But if you want to do this right, you have to go through this trouble, and finally it allows you to do stuff that is really hard in other languages. Ruby 1.9 also fixed these problems. 1.8 was still using like 8-bit bytes everywhere. Ruby 1.9 has many incompatible string types, because a string in Ruby is a tuple of the encoding and the actual data, because they can't or they don't want to use just Unicode internally for political reasons. We can talk about those like outside. But it means that in Ruby, it's up to you as a developer to decide what you want to use as an internal representation of your strings. And then they have methods to convert between the encodings where it is possible. Perl has always done this right since the beginning. Swift was really funny when they introduced this at WDC. I watched some of the videos, and they had a guy on stage that was confusing graphemes, code points, and bytes, which was scary. It was 2014. I mean, you would expect them to know that. But in their defense, they have fixed all of this, and now they have a really cool string API that actually helps you there. If you're using C, then I would point you at ICU, which is a Java thing, but they also have a C wrapper or a C counterpart to do this. And for JavaScript, like, what are we doing there? ES 2015 has provided us with solutions for problems. The thing is, of course, you cannot change string.length, because people might be relying on these like wacky counting So what you can do is using new syntax. You can treat your Unicode string as a sequence of code points. Unfortunately, still code points, we'll see that. And then you can take the length of that sequence, and that then gives you the correct answer. This pile of poo only contains one code point. The B that you see there is unfortunately Node.js or Chrome. Nobody supports this yet. This has been transpiled using Babel.js, and I just wanted the screenshot to look nice. It's like a little wrapper. Regexes have the same problem as before. This hasn't changed. It can't change without changing the regex itself, again, because of backward compatibility issues. In this case, you just append a U at the end of your regular expression to tell the regular expression engine to treat this, the input string as a real Unicode string instead of this like UCS2 hack, and then you get the correct result. So if I match one character on this pile of poo, then I get my one character back and the one that I have expected. Unfortunately, there are still some bugs. This is probably in Babel.js. I haven't investigated. I might report this. You are supposed to be able to normalize strings. That this is an A followed by a combining diaresis, and I normalize that using the most compact normalization form there is, which should turn this into a small letter A with diaresis. Unfortunately, it doesn't. It still has a length of 2. I would hope that this gets fixed. Otherwise, we basically cannot really normalize strings. And this was explaining you why the length of the pile of poo is 2. But all around these Unicode issues, there is a huge list of additional things that I cannot also squeeze into the time we have here. There is a huge thing around localization issues, because some operations that you would think you can apply now, that you know what is a string, how is it stored, how do the algorithms work, you would think you can apply some operations universally. In fact, you can't. Collation is location dependent. Case change is location dependent. In Turkey, there are other rules than here with regards to the letter I. So this is kind of tricky. I have talked about this last year in Swiss.js. This is a JavaScript conference here in Switzerland. There are security issues because you can have different code points for different languages that look the same or nearly the same. And so you could have register for, or you could back then register for an SSL certificate for paypal.com, but the last A was in fact not really an A, it just looked like an A. And so if you are a certificate authority, by God, I hope you don't have to do this, then you suddenly have to take care of this. You can't just blindly issue certificates. You have to really check them, and you have really special rules for different languages, different character ranges that you have to keep in mind. Otherwise, you're signing the fisher's heaven, basically. So this is really tricky. And then this is my favorite part. This is all around software is broken. We have seen the broken normalization. My really favorite thing here is the term US UTF-8. So you're a US company, you were using ASCII, and you say, okay, it's the 2010s, maybe we should move forward. And then you say, okay, we convert to UTF-8. And if you're in an English-speaking part of the world, all you have to do is change from content type ASCII to content type UTF-8. Now I'm done. because of these like compatibilities. Of course, this only works in like the English areas, and the moment you leave, stuff will start burning and like going up. So this is the term that I'm like referring to when this stuff happens. You see that when you get a delivery from the US, like we ordered some servers at Dell and they just cannot write our address correctly. And it's also funny when you look at it, it is like always a bit different, but always wrong. If you are into this, and you really have to be into this, then I recommend you this book here. But once you have read it, it's not the most like uplifting literature ever, but once you have read it, then you know everything there is to know about Unicode. So if you have any kind of interest in this, or even better, if I kind of awoken some interest, then maybe this is something to read. And before I'm leaving, I have a little quiz, because you know now how this works, right? I have explained everything to you. You know how Unicode characters can be composed of different code points, you know how these lengths work, and you know how all of this works. So I have these two emojis here. It's the same. It's two kissing men. I want to take the length of it, the traditional way, and I want to get like the ES6 length in code points. So you can like think about this while I'm taking a few questions, and maybe you find out how it works. Questions? Yes, you are. You are. So the question was, what do you do if you're not using one of these languages where it's correct? Are you screwed? Yes, you are. You cannot use the APIs provided by your language. There are external libraries that you can use, and you probably should use, unless you want to end up on a slide of mine when I'm laughing at your counts of underscores. So you have to use external libraries. For JavaScript, by now it's being fixed. Maybe, or actually I know that Java 8 has some improvements that were made, but it is different API because the existing stuff cannot be changed for backwards compatibility reasons.
I had a second question. You said that Perl has always gotten it right. Does that mean that they were always calculating with graphemes instead of code points or bytes?
Now, getting it right means you need to offer at least 3 count methods. Because depending on what you want, you might want graphemes, or you might want the code points, or you might want actually the byte length. So getting it right means I need all these methods of counting. And Perl does. You have to include the or whatever encoding package that you need. Then it turns on Unicode mode, and then you have APIs where you can ask the right questions, and then you get the correct answers. So just, those emojis. The length is 11, of course. And the ES6 length, of course, is 8. And some of you might have known that, and that's really impressive. Because the character is actually a combination of a few characters. You have an emoji, you have a zero-width joiner, which means that the thing that comes afterwards should be put on top of the character that was there before. You have a heavy black heart. You have a variant selector that chooses the skin color. You have another zero-width joiner to add the kiss emoji on top of it, and then another zero-width joiner to add the other man on top of it. And if you count these as traditionally to get the length, how JavaScript would have done it before, you have 2 for the emoji, 1 for the zero-width joiner, 1 for the black heart, 1 for the variation selector, 1 for the joiner, 2 for the emoji, 1 and 2. And if you do it in the new way, then everyone is just 1. But there is still this like combining marks. So yeah. Thank you very much. I hope you enjoyed it, and I hope you have many, many more questions, and I hope you know that all you thought that, oh, this was so easy is actually not really easy, and there is a lot of stuff we have to get right if we want to really get it right.